Welcome back. We're going to continue our studies on conic sections and ellipses by studying eccentricity. We're going to define eccentricity of an ellipse. We're going to do some samples of that, and then we'll use our graphing utility. But let's take a look at a little background on eccentricity. One of the reasons it was difficult for early astronomers to detect that the orbits of the planets are ellipses is that the foci of the planetary orbits are relatively close to their centers, and so the orbits are nearly circular. To measure the ovalness of an ellipse, we can now use the concept of eccentricity. We'll have ellipses that are more oval or longer or taller as opposed to more circular. Our definition of eccentricity, E, of an ellipse is just the ratio E equals C over A. And recall that C is the distance from the center to the foci, and then A is the length of the distance from the center of our ellipse along the major axis. E is going to fall somewhere between 0 and 1, non-inclusive. If E is closer to 0, then we have a more circular ellipse, and if E is closer to 1, we'll have a more linear or longer or taller and skinnier ellipse. Let's take a look at a sample. Given the ellipse defined by the equation below, determine the eccentricity. Based on our denominators here, we can see that our A value is 4 and our B value is 2. So working down the page here, using c squared equals a squared minus b squared, we can substitute our a and b values in, and we get c squared is 12, and c is, once again, the square root of 12. Substituting into our formula, e equals c over a, so e equals the square root of 12 over 4, or 2 square root of 3 over 4, or the square root of 3 over 2. This is about 3.5 over 4, so we would expect this to be a relatively narrow ellipse, or less circular anyway. Our third objective is to use the graphing utility to graph an ellipse. So let's take a look at our ellipse x minus 1 quantity squared over 2 squared plus y plus 2 squared over 4 squared equals 1. We want to write the equation in complete the square form. So we're going to go backwards here. So we're going to get rid of the fractions, and then we'll solve for y squared. We'll square root both sides, so then we can solve for y. We'll get two equations, and we'll graph this just like we graphed our circle. So in this particular example, with a denominator of 16 and 4, if I multiply both sides or everything by 16, the 16s will cancel, but here I'm left with 4 in the numerator, so after I multiply by 16, I'm left with 4 times x minus 1 quantity squared plus y plus 2 squared equals 16. I'll subtract the 4 times x minus 1 quantity squared from both sides, and I get y plus 2 squared equals 16 minus 4 times the quantity x minus 1 squared. Then square rooting both sides, I get y plus 2 equals plus or minus the square root of 16 minus 4 times x minus 1 quantity squared. I subtract 2 from both sides. I'll put that 2 right in there, and I get y equals negative 2 plus or minus the square root of 16 minus 4 times x minus 1 quantity squared. So now I will have two half ellipses that I'll want to put into my graphing calculator. I'll do the top half, y1 equals negative 2 plus the square root of 16 minus 4 times x minus 1 quantity squared, and y sub 2 will also equal negative 2, but now minus the square root of 16 minus 4 times x minus 1 quantity squared. So I'll graph these two simultaneously in my graphing calculator. I'll use the zoom square or a square window setting to get a nice picture. So I've taken the liberty to go ahead and insert our two equations for our ellipse, the different halves. Under y1, I've got my negative 2 plus the square root of everything. And under y2, my negative 2 minus the square root of everything. I want to graph this in a square window, so I'll hit zoom square. And I've got a pretty good picture of what that ellipse might look like. If you want to play with your window and make that a little better, feel free to do so. You'll get plenty of time to practice more of this when I see you in class.